Welcome everyone to lesson 2.8 from Precalculus, which is all about inverses of functions, aka inverse functions. Let's get started. So a function f has an inverse function we call f inverse, which is denoted by the f itself having a power of -1. It's not an exponent, but I digress. If each output of f is produced from a unique input, meaning that functions themselves have to exist if every input has a unique output. What this is saying is for inverse functions to exist, every output has a unique input, essentially meaning the functions are what's called one-to-one, where every number is paired with exactly one other number. So what this does is it's an inversion operation. It switches the mapping of the function, aka it switches what is an input and an output. So an inverse would take f of a equaling b, and it would become f inverse of b equals a. So it's what do we need to do to the output to get the input that produced it, is essentially what it's doing. It's undoing everything that the function itself does. So it takes a point ab and makes it ba. So it's switching those inputs and outputs, undoing whatever the function is doing to the inputs. So how do we see if we can actually take the inverse of a function? Because not every function can you take the inverse of. So analytically, what that would look like is you would look at the behavior, and you would know what the behavior of essentially what these functions should look like. And if the function increases or decreases only, there is no place where it switches from increasing to decreasing, then it's invertible. Graphically, we would do what's called the horizontal line test. If we can draw a horizontal line through every single point on that graph, and it only touches the curve once, then it's invertible. And numerically, what that means is that the output value is not repeated. So if we see the output value twice, it's a pretty good indication that it's not invertible. The analytically is going to be pretty hard unless you have a firm understanding. So for the easier functions, it's a little bit easier to understand. When you get to far more complex functions, then you got to think a little bit more. So let's do some problems with this. So we have a function f, and what we're going to try to do is we're going to try to label some points, figure out the points would be on its inverse, and then plot those points and see if we can graph a new function. So for this graph here, it looks like we have a nice point here, a nice point here, 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 and that looks like it's it. So those points are -4, and that would be -5. We have -3, 2. We have -2, 3. And then we have -1, 4. So this function is invertible, and I can tell that graphically because it passes the horizontal line test. So let's invert the points. So instead of being -4, -5, it's going to be -5, -4 for the inverse. 2, -3, 3, -2, and then 4, -1. I don't know why that moved. Better. All right, so, and that was 4. So we're going to plot these points now and see what's different about them. So I will graph them in red so we can kind of see them. So -5, -4 is here. 2, -3, 1, 2, 3 is here. 3, -2, 4, -1. So we get this curve here. And graphically, that looks kind of strange. An important note is that all inverse functions are essentially a reflection over the line y equals x. So I missed. So they are a reflection across this line, which is y equals x, or the identity function that we talked about before. So that's kind of cool. So are these functions invertible? Well, we can draw a horizontal line and move the horizontal line and see if it would intersect the graph any more than once. And it does not here, and it does not here. It looks a little sketchy around here, I'll give you that, but it does not in fact, intersect twice. And we know it because it's a cubic, and if I think about a cubic, every time I cube a number, I'm going to get a different number. And if I cube something, there's only one unique cube root of it, so on and so forth. So what we can do is we can take some points and steal those. We can also take this idea of a reflection over y equals x, but I find that to be a little bit more difficult to try to do offhand. So what I'm going to do is I'm going to mark some points, some nice points we have. And then I'm going to flip those points. So 0, 0 flipped is 0, 0, 1, 1 flipped is 1, 1. But this is 4, 2 is going to be 2, 4. So this looks like that. A little bit more curvy, but you know, it works. This function here has a point here, here, and here. So this is negative 2, negative 4, so it's going to be negative 4, negative 2, 0, 0, and this is 2, 4, so this is going to be 4, 2. So this function is going to look like this. Or it's going to be a little bit more curvy in the middle, but you get the idea. A lot easier to do in pencil, a lot harder to do on a tablet, but I digress. So if we take the inverse of a function, its domain and its range are going to swap. That's the next big idea. So if we're given the graph of f, and we're trying to find the minimum value and the maximum value, we have to remember that our domain and range have swapped. So domain is now your y's, and your range is now your x's. And values are ranges, are typically the y's, the outputs. Well, the output is the input. Yeah. So we're looking here and here. So our minimum value of f inverse is negative 1, 2, 3, negative 3, because it's the lowest x of f. And our maximum value of f prime would, not f prime, f inverse, thinking derivatives, is 6, because the largest x value is 6. I apologize now. I will probably in class say f prime a lot, because my brain's programmed for calc, but f inverse, you just have to correct me. I'm prone to making mistakes too. So to find an inverse analytically, it's not bad at all. What we're going to do is we're going to take the f of x value, or f of x part of the function here, and we're going to replace that with an x, and we're going to replace this x with f inverse, or for right now we can use a placeholder of y. I like doing that because I'm lazy and don't like to write as much. So there we go. But typically for functions we solve for the output, so we're going to solve this for y. So that gives this x take away 3 is equal to y plus 2 cubed. So the cube root of x minus 3 is equal to y plus 2. So f inverse of x is equal to the cube root of x take away 3 plus 2. Not bad. What if we have a function that is not naturally invertible? If I look at this function here, it is a quadratic. It produces a parabola, a beautiful U shape. But the problem with U's is that they are not one-to-one. So what we have to do is we have to make the function one-to-one. And we have to use what we know about the function to do that. I know that a quadratic is symmetrical. So if I can find the x-coordinate of the vertex, then I can just take the right side of it, and then I'm good. So in this quadratic, and remember, you can always find the x value of a vertex by doing negative b over 2a. That would be negative 0 over 1, 0. So the x-coordinate of the vertex is 0. So we're going to restrict this domain, and we're going to say its domain is going to be 0 to infinity. So instead of a quadratic naturally going from negative infinity to positive infinity, we're going to say this quadratic, we're starting at 0 and going up. Now we can do the same process we did with the other one analytically. Replace the x with a y, the f of x with an x, solve, and there we go. We shouldn't have any more problems. So what does that look like? We have x is equal to 1/2 y squared plus 2. We're going to subtract 2 and then multiply by 2, so we have 2x plus minus So we have 2x minus 4 is equal to y squared, which means that y is equal to the positive or negative square root of 2x minus 4. That's a problem. That's where we get this it's not naturally invertible piece from. But we did make a decision beforehand. We said that we were going to take the x-coordinate of the vertex and everything right of it. So, because we chose the right, we're going to keep the plus and we're going to ditch the minus. We don't need it because we've restricted ourselves to positive inputs. So, the range of this function should be 0 to infinity, and in fact, it is. So, f inverse of x is equal to the square root of 2x take away 4. What is the domain and range? Well, the domain, well, it's a square root. We can figure that out. We set the inside of the square root greater than or equal to 0, which means that 2x is greater than or equal to 4, which means that x is greater than or equal to 2. So its domain is 2 to infinity. Its range is the domain we restricted before. It is this 0 to infinity. So 0 to infinity. Not bad. So let's do that more. Let's get more practice in. In fact, I would love for you to pause the video and try some of these out on your own and check yourself against me. But I digress. I'm going to go and I'm going to get x equals the square root of y take away 3 plus 2. X take away 2 is equal to the square root of y take away 3. X minus 2 squared is equal to y take away 3. So f inverse of x is equal to x take away 2 squared plus 3. Its domain would be the range of this function. So the range of this would be, lowest thing it outputs is 0, plus 2 would be 2 to infinity. Its range would be the domain of f, and the domain of f is 3 to infinity. Not too bad. Fractions, always love fractions. So let's try this one. We get x is equal to 3 over y plus 6. So x, y plus 6x is equal to 3, which means that xy is equal to 6 is equal to 3 take away 6x, which means that f inverse of x is equal to 3 take away 6x over x. So what is its domain? Well, its domain is it cannot be 0. So negative infinity to 0, 0 to infinity, and that's pretty easy to see from the inverse itself. The range, well, we can look at this function here. It can't have a negative 6, so negative infinity to negative 6, negative 6 to infinity. There are other ways to tell, and I would love to pick your brain about in class. The last one is kind of weird because we have two x's. Both of those become y. So x is equal to 2y take away 3 over y plus 4. So xy plus 4x is equal to 2y minus 3, which is going to become xy take away 2y is equal to negative 4x take away 3, which means f inverse of x is equal to negative 4x minus 3 over x take away 2. If you weren't able to follow all of my steps, that is a-okay. I simply just ask that you ask me about it in class. All right, so its domain, well, it can't have a 2. So negative infinity to 2, and then 2 to infinity. Its range, well, h can't be a negative 4. So negative infinity to negative 4, negative 4 to infinity. So I know that I mixed some of these up. This one's G, so this would be G inverse. This is H, so this would be H inverse. I'm not going to go back and change it now, but I did notice it. Sorry. Hopefully that wasn't too bad. The last thing we're going to talk about is how to verify that two things are indeed inverses of each other. So how would you do that? You would compose them. If you do the composition of them and you get the identity function, if you get X, that is how you verify if two things are an inverse. It's how you would prove it, essentially. Something a lot of students like to do is they like to take one and find the inverse of it to be the other. You can do that, but there are weird domain restrictions that we've talked about before, so this is the easiest way. So what we're going to do is we're going to do f of g of x, which is equal to 2 over x, take away 3, plus 3. It's pretty easy to see that the minus 3 and the plus 3 would cancel, leaving us with 2 over x. Here's where you would multiply by the reciprocal, keep, change, flip if you will. So that would be equal to 2 over 1 times x over 2, which is x. So yes, they are inverses, and that is why. So again, I would always use composition to check. It might seem easier to take the inverse sometimes, but use composition. It's a nice, easy way to verify. That is it for us. If you have any questions, please let me know in class. Otherwise, I'll see you in the next video.